This is true only in an inertial frame of reference. So the second condition necessary to achieve equilibrium is stated in equation form as net torque equals 0, where net means total. Torques which are in opposite directions are assigned opposite signs. A common convention is to call counterclockwise or the CCW torques positive and clockwise or the CW torques negative. So og counterclockwise siya, ang equivalent sa torque is positive. But then og clockwise, ang iyang equivalent sa torque is negative. Always remember that. So for example here, when two children balance a seesaw, as shown in figure 9.8. So they satisfy the two conditions for equilibrium. Most people have perfect intuition about seesaws, knowing that the lighter the child must sit farther from the pivot and that a heavier child can keep a lighter one off the ground indefinitely. So, ang ang mas layo sa seesaw, mao siya maong mas bugat pa. So kani for example, muna siya sa katunay child na naa sa seesaw. So the first child has a mass of 26.0 kilograms. Sits 1.60 meters from the pivot. If the second child has a mass of 32.0 kilograms, how far is she from the pivot? And B, what is the force sub P, the supporting force exerted by the pivot? So here, the strategy mo na siya. Both conditions for equilibrium must be satisfied. In part A, we are asked for a distance. Thus, the second condition regarding torques must be used, since the first, regarding only forces, has no distance in it. To apply the second condition for equilibrium, we first identify the system of interest to be the seesaw plus the two children. We take the supporting pivot to be the point about which the torques are calculated. We then identify all external forces acting on the system. So, muna siya ang solution. In solution A, the three external forces acting on the system are the weights of the two children and the supporting force of the pivot. Let us examine the torque produced by each. Torque is defined to be torque equals RF sine theta. Here, theta is equals to 90 degrees so that sine theta equals 1 for all three forces. That means R is perpendicular equals R for all three. The torques exerted by the three forces are first, the torque sub 1 equals R sub 1 and W or the weight sub 1. Second, torque sub 2 equals negative R sub 2 and then times W for the weight sub 2. And third, torque P equals R sub P and F sub P. So equals 0. F sub P. Then, ang answer is equals to 0 muna siya. Note that minus sign has been inserted into the second equation because this torque is clockwise and is therefore negative by convention. Since force sub P acts directly on the pivot point, the distance R sub P is 0. A force acting on the pivot cannot cause rotation. Just a pushing directly on the hinges of a door will not cause it to rotate. Dili siya mo rotate. Now, the second condition for equilibrium is that the sum of the torques of both children is 0. Therefore, torque sub 2 is equals to negative R sub 1. So, 0 iyahang equivalent sa torque. Or R sub 2 times R sub, weight sub 2 equals R sub 1 and then W sub 1. Weight is mass times the acceleration due to gravity. In pairing mg for W, we got R sub 2, m sub 2, g equals to R sub 1, and then m sub 1g. So m is the mass. Solve for this for the unknown R sub 2. R sub 2 is equals to R sub 1, m sub 1 divided by m sub 2. So the quantities on the right side of the equation are known. Thus, R sub 2 is equals to plus parenthesis 1.60 meters, open parenthesis, plus and open parenthesis 1.60 meters. So, 26.0 kilograms, man siyang equivalent sa katong na concept child sa siso. Divided by 32 kilograms, 32.0 kilograms. So, the answer, 1.30 meters. As expected, the heavier child must sit closer to the pivot. So, 1.30 meters versus 1.60 meters to balance the seesaw. So, man siya, para mabalance ang seesaw, kana siya maoy ko anon. So, for solution B, this part asks for a force, or the F sub P. The easiest way to find it to use the first condition for equilibrium, which is net force is equals to 0. The forces are all vertical, so that we are dealing with a one-dimensional problem along the vertical axis. Hence, the condition can be written as net force along y, or the y man was a y-axis equals to 0. Where we again call the vertical axis the y-axis. Ano siya, may y-axis ang yung vertical. Choosing upward to be the positive direction and using plus and minus signs to indicate the direction of the forces. We say that F sub P minus W sub 1 minus W sub 2 equals to 0. So, kanang W is the weight of the object. This equation yields what might have been guessed at the beginning. So, F sub P, or the force sub P, equals to W sub 1 plus W sub 2. So, the pivot supplies a supporting force equal to the total weight of the system. So, entering known values gives F sub P equals to M sub 1G plus M sub 2G. So, the mass ng M. So, F sub P is equals to, open parenthesis, 26.0 kilograms, close parenthesis, times 9.80 meter per second squared. So, plus, kaya na po, open parenthesis, 32.0 kilograms, close parenthesis, times, open parenthesis, 9.80 meters squared. Meter per close parenthesis. So, ang yung answer is 568 newtons. Ano siya ang answer. So, for the discussion, sa katanay mga example sa problem solving, the two results make intuitive sense. The heavier ang mas bugat, may katong naglingkod closer to the pivot. So, the pivot supports the weight of the two children. And the part B can also be solved using the second condition of equilibrium, since both distances are known, but only if the pivot point is chosen to be somewhere other than the location of the seesaw's actual. The preceding example have broad implications. First, the choice of the pivot as the point around which torques are calculated simplify the problem. Since force sub P is exerted on the pivot point, its lever arm is 0. So, 0 ang ihang equivalent sa lever arm. Hence, the torque exerted by the supporting force, or the F sub P, is 0 relative to the pivot point. The second condition for equilibrium holds for any choice of pivot point. And so, we chose the pivot point to simplify the solution of the problem. Second, the acceleration due to gravity cancelled in this problem. And we were left with a ratio of masses. This will not always to be the case. Always enter the correct forces and do not jump ahead to enter some ratio of masses. Third, na kinahanglan hinumduman, the weight of each child is distributed over an area of the seesaw. Yet, we treated the weights as if each force were exerted at a single point. This is not approximation. The distances R sub 1 and R sub 2 are the distances to points directly below the center of gravity sa katong duha ka child. Finally, note that the concept of torque has an importance beyond static equilibrium. So, torque plays the same role in rational motion that force plays in linear motion. So, that's all for my report. Thank you.